Okay, so it's 2 minutes past 10, so welcome everybody to this webinar regarding the use of FIWARE platform and smart data models for water management. So thank you everybody for joining, and thank you especially to our speakers, Sweetapple and Franck Gall, which will be talking after me. Okay, I will introduce a bit the question for making those of you who are not familiar with FIWARE platform and FIWARE data models, what are they going to talk about? But the interesting point are their presentations. So this is the index. I will introduce the context, the learning goals of the session, and I will make some simple questions to start and what will happen to your data models regarding water management, and 5 simple questions to describe the initiative and what is the structure, the data models life cycle, and the services that we offer to the users regarding the smart data models. So first of all, you have to be aware, most of you are, but possibly there are somebody who's new, that FIWARE was created to support a smart digital life and to create a standard for managing the context or to create digital twin data. So we are present in many domains, and smart water is one of them. And what we provide is the ability to interconnect all of them in order to provide additional value for our users. So the learning goals is just, on one hand, to provide some context for the coming presentations, understanding how the data models can help you on the water management, okay, understanding what's the initiative about, and how to use it and how to contribute if it is the case for you. So first simple questions is, if you are managing water data, or you are going to, okay, then you are in the right place. Possibly you'll have to integrate data coming and going from very heterogeneous system. When I mean heterogeneous, I mean it could be a legacy application, could be an array of sensors, could be other third systems, and what we provide is an easy way of connecting them and providing context information. And of course, possibly you have to meet some regulations or the specifications of some tools like EPANET that we'll talk later, and you don't have precise information, or you don't want to do it alone. So and let me explain why the Smart Data Models initiative exists. So because if you have to integrate such systems that we have talked in the previous slide, and you create these data models for the connection, what will happen to them when your project ends, or when you have to update it, or when you are asked to make it interoperable with other new initiatives or applications, or you need to update to new regulations and so on. The point that we offer is that it will be much more efficient to do it together with some other people who share the same needs that you do, and to just with tiny efforts from a big community, then you get all the results at the part of the cost. Okay, 5 simple questions about the Smart Data Models initiative. So we are a community site with detailed data models because otherwise we won't be able to meet the goals of providing data models which can evolve at market speed, okay, and based in real case scenario. Is not a FIWARE only initiative. So currently TM Forum is in the technical steering board, but there are many other organizations, especially in the water domain, and you will see a couple of them today, helping on the creation of these data models. So FIWARE Foundation is not the one creating the data model, but kind of fostering a bit these data models. What are the advantages of using them? So we check for the coherence and consistency, and we provide an agile standardization. So we don't have these lengthy standardization cycles that you have in a regular standardization body, but something which is more flexible and more agile, reducing this way the time that you need for coding. What happens if these data models does not meet your needs? First of all, we try to make it the more flexible that we can. Okay. Of course, all of them are open license, and therefore you can modify, adapt to your needs. Okay. And if this was the case, you can contribute these data models in order to find some other help. Okay. And where can you find these data models? You have there in GitHub, and you have also a web page for the users in smartdatamodels.org. So this is the organization. We have an umbrella repository. We have a specific domain for smart water, and inside that domain we have several subjects, which are groups or directories into one repository in GitHub, compiling these data models. In fact, what you are seeing on the left part of the image is the actual domains. Okay, there is a specific domain for smart water, and inside this smart water, currently there are 4 subjects. Okay, the more populated is the water network management, that is expanded into the right part of the image, in which you have 9. In fact, it's growing, and there is two more data models coming. Okay, so keep looking at the webpage, because it's constantly growing and evolving. So what is the life cycle of these data models? So you can start creating data models into the incubator repository, which is kind of an open repository for people to start doing. Then if you meet minimum requirements, you can jump into the harmonization repository, which is something for those data models which are accepted, but not completed the documentation required for the data models. And then once you meet all the requirements, you jump into a subject like these 4 that you see in the previous slide. And last point, what services do we offer to the users? First of all, you have a front page with everything, with every update regarding the data models. We also provide a database that allows you to look for if there is attributes or enumerations for creating your data models, and do not reinvent the wheel. If you are looking for the description of every concept, there is another database with descriptions. Of course, you have a subscription service with a specific domain for water. And we provide support to the users that you raise into GitHub or the pull request if you do it. Of course, in this web page, you can also submit your data model, not only by doing a pull request. We have certain training materials. You see in the right part of the slide some examples on how to do it, how it is licensed, the governance and the roadmap. And we provide also a contribution manual to make it easier to contribute, and providing links to the templates, to the examples, and some guidelines additionally. And last but not least, we have a contribution agreement which grants you that the data models that you use have all the rights to be licensed with an open license. Okay, so with this, I hope that you have a clear picture of what is the Smart Data Models Initiative, and therefore you are in good condition in order to understand what are our speakers, Franck, Gall, and Chris Sweetapple is going to talk to us right now. Okay, and questions and answers will be done by the end of all the speech, after Franck's and Chris' speech. So thank you very much. And now I guess this is Franck's turn, isn't it? Okay, I'm going to mute it.
Hello, Franck Gall from AUGMENTED. Thank you, Alberto. So on my side, I will give you an overview of what are ongoing activities to provide data models related to the water domain and align with the framework that Alberto was presenting just before. So first, a quick introduction. So myself, I'm Franck Gall from AUGMENTED, SME, quite involved in the water domain. And in several groups. And AUGMENTED, we are a FIWARE Gold member, so quite involved in that community. All these activities are quite supported by a number of different research projects funded under the H2020 program of the European Commission. And it's all organized within a research cluster, ST for Water cluster. So I wanted just to put some light on this cluster, because that's a place where a lot of discussions are taking place. It started about 8 years ago, and now it's more than 45 EU projects which are cooperating together. And this cluster is having a number of synergies with other activities. So for us, it acts as a multiplier. So this is quite important when we are working on data models, because it helps getting adoptions of these models. And this cluster also developed or drafted an action plan that you can find on the net, describing, okay, what are the intended activities. And all these activities are managed by a number of working groups looking at standardization, data sharing, and so on. And so on. Among these activities, one has been to look at the water life cycle. I will not enter into the detail of all the water use cases. You can find them, many of them, in that nice picture. And you can find also the name of a number of projects which are contributing to it. And what is interesting and appear, let's say, over the last year, is that a number of projects were interested in working with FIWARE as a platform for data exchange. And we organized, beginning of 2020, a first workshop discussing data models for water, which groups several projects: FIWARE for Water, Score Water, NIADES, Aqua 3S, and Digital Water City. And from that point, we agreed to move together and developed a model for the water domain. This obviously is open to other projects, so do not see that as a closed initiative. As Alberto was saying, we want to share because that's how we will achieve interoperability and data sharing. So if you are interested to join, please contact us after the webinar. I will now go into more a bit more technical details about what we are doing, starting with the device. It always looks simple, connecting a sensor, but when we are looking at it from the data modeling perspective, it's not that simple. So quick reminder, the models we are developing are based on the NGSI LD specification, which is developed by the ETSI, and in ETSI a group named ETSI IGC, which is Industry Specification Group for Context Information Management. And this group has defined an information model, which is graph-based, and which has as core concept entities connected through relationships. And entities can have properties and relationships. But relationships and properties can also have properties and relationships. So this allows to build a complex property graph of information. And in that model, we can also reference to define hierarchical vocabularies, ontologies, so to make sure that terms are defined unambiguously. And it also allows other users to bring their own model, so to make use of familiar definitions. And in addition to the model, but it's not really the purpose today, there is an API where you can do queries and subscription over the model with a query language for it, not completely open, but to make it more predictable, because at each time when we're developing these, the idea is to think about implementations, to make it implementable. Now let's look at the device model. So you can you have the link in the GitHub. It's part of the framework that Alberto was just showing before. And then you will find the device model, so a description of what is the device, and then description of the model. You have an ID, obviously, the type, which is of type device, and then you can define a number of parameters which are either optional or mandatory. So when you do your own use of that model, you can pick up the categories which fit your use case. And on the right, you see how it appears when expressed or serialized using JSON-LT, which is the standard used to transport NGSILD payloads. Okay, so this is quite self-readable, I assume. You have a bit of knowledge of that. So now the ideas, problem we had, one of the projects named FIWARE for Water was to connect smart meters. So it's about 100 smart meters somewhere in the south of England, connected to a Sigfox network. And the need was to connect these devices to the FIWARE platform. So first we had to model the smart meters, and this is an extract of what we do. So for each smart meter, we will use a model like that, which is one is a graphical representation of what I was showing before. So each smart meter obviously has a location. It can control a number of properties. These are the measurements smart meter can do, or the alarms it can raise. It has a name and some information about when it was installed, calibrated, and its number. So this is okay done. We have the smart meter model. Now the question is, this smart meter is going to measure some parameters like water consumption of somebody, and the question is how to connect this device to the consumer. And there are some good practices. So you can see on the picture here, you recognize the model of the device, and on the bottom you can just see a quick model we do to model a consumer, or consumer house if you prefer, which has a property named water consumption and some properties or some values of water consumption, a unit code, because there's a unit code in NGSILD to be specified, and a timestamp, which is the date of observation. And what is important is that all measurements which are being done by the smart meter are not attached to the smart meter. Okay, we attach them to the water consumption property of the consumer. And two reasons for that choice. First, we see that the measurements themselves are attached to the consumer, not to the device doing the measurements. And this is good to help supporting the data ownership and to support the privacy protection, because we know where is the consumer data. And more important from implementation point of view, it is queries like, okay, what is the consumer water consumption? Okay, you think here we have a simple graph. Think about a graph where we have hundreds of meters and so on, and consumers, and we want to find how much these consumers are consuming water. This is direct connection. I know my consumer, I can ask for his consumption. Okay, so in my graph, it's fast for the query. So this water consumption is being updated by all smart meter measurements. Well, so when the smart meter does a new measurement, it updates that property directly. And obviously, we have this observed at value, which is the timestamp of the measurements, and which allows the system to create the time series of measurements. So in practice, we move forward on the development. So we have on the left the Sigfox backend, which is running with about 100 smart meters, and in the middle we have components from the FIWARE catalog. We have a Sigfox IoT agent, which is meant to transform the Sigfox payload into NGSILD1. This is sent to a broker, which has obviously some security layer. And so at the end, data can be consumed by a dashboard or an application. So first, when we have set up that system, obviously we have to register the device. So the smart meter devices I was showing just before, we create these devices into the system, into the broker. And once they are known by the broker, then we can just configure the Sigfox IoT agent, which will, when it receives some data like that from the Sigfox, here you can see this is the payload we receive from the Sigfox network. We have to decode it to make it meaningful, and at the end being able to get the data over the dashboard. So this is kind of simple, let's say, deployment that we do. next, and also to introduce the next speaker presentation, how to go further. Now we have our physical system. It can be a water distribution network. It can be a wastewater treatment plant or anything like that. It has its own definition, and it has some sensors in it. So from that, we can build or create a digitalized description of that asset. And it's maintained up to date within the brokers through the sensors. So the sensors, the devices are providing information about that asset, and we can query in real time, okay, what is the height of water in that tank? What is the pressure in that pipe? What is the chlorine level there, and so on and so on. So this is real-time representation of the system, and it's let's say virtual representation or digitalized representation description of the system. We don't have when a user wants to know, okay, what is the pressure of the system? I don't want to go and query the system directly. My FIWARE environment is holding the latest value. Okay. Now the idea is to go a bit further and to be able to do some sensors composition, to add virtual sensors. For example, you can have a system where you have several pipes with pumps in parallel, and you would like to assimilate these to only one big pipe with one big flow. Okay, so you can create or compose these different systems, these different parts into one virtual sensor that will give you the overall flow in that set of pipes. And then also to go a bit further, you can add a simulator. Simulator will, knowing all the parameters of that system, is able to do some calculation, to do some prediction about that system. And what it is used for is for the user to do some anomaly detection. So this means that I get the measure, the actual measurement from the system. I can run in parallel the simulation, and do I see for any part of the system some strange behavior which are unexpected and which could raise an alert. The second one is to, for example, to run predictive evolution analysis. I know that system is in that stage today, or is it going to be in 2 hours? So this again using the current state and the simulator. And one step further, what if scenario? Okay, I have my system. I want to close the valve. What is going to happen in my network, or the pressure are going to propagate in the network? And this is kind of scenario we have to handle. And this, I would not yet call it digital twin. We are heading toward it, but I'd like to call it an augmented virtual representation of my system. And this is to introduce the next speech from Chris, which will present you a bit more in detail what we are doing in that direction. So I thank you for your attention, and will be pleased to answer questions at the end of the webinar. Thank you.
Okay, thank you very much, Franck. So I encourage the people attending the webinar to take note of their questions, and by the end we will have a period for question and answers. And now I want to welcome Chris Sweetapple from the University of Exeter. Please, Chris. We are not hearing you.
Sorry, hopefully you can hear me now.
Now, yes, thank you.
Good. So I'm going to talk about a specific example of using smart data models for water. This is linking EPANET to FIWARE. So first thing to answer is what is EPANET? So EPANET is a program that's widely used for modeling water distribution systems, both in industry and research. It also provides the foundation of several commercial software packages for water distribution system modeling. It allows us to model hydraulic and water quality behavior of a piped network. So it's able to provide the user with a lot of information about performance and conditions throughout the network, potentially based on a range of different scenarios. So it's a very useful tool. It can provide outputs like flow rates in the pipes, pressure throughout the network, how much water is supplied, etc. So why do we want to link it with FIWARE? Well, conventionally with EPANET, simulations are run from an input file that contains a fixed description of the network and its starting state. Obviously, in reality, things like tank levels and demands are constantly varying. So if we want to make best use of this model, we need to be able to update it with real-time data. So at the moment, this isn't particularly straightforward, particularly as the data that's available will vary from system to system. If it's coming from different places, it's likely to be in different formats, and it might not always be very easy to map to the relevant parts of the system. So hopefully by linking EPANET with FIWARE, all of our data, including the actual EPANET model, will be available in the same place. It should be much easier to access the data that's relevant, use this to update the model in real time, and help improve our operational management of the system. It could also make it easier to do things like simulating different scenarios. For example, if historical demand data is available through FIWARE, and so is the EPANET model, it would be much more straightforward to feed that data into a simulation. So the first step for integrating EPANET and FIWARE is converting the EPANET model data to an appropriate format for managing with the FIWARE context broker. So as you've heard, or as you know, there are various different data models already for different applications. And in this case, we've developed a new water network management data model. So in EPANET, there are lots of different network components that can be modeled, like pipes, pumps, valves, etc. And the new water network management data model reflects this structure. So, so you can see here a screenshot from the data model repository, which shows some of the different network components that are included in the data model. So like how a network is described in EPANET, this includes separate entities for each type of physical network component. So you've got your junctions, tanks, reservoirs, pumps, valves, and pipes. And you've also got curve and pattern entities that help describe the operation of the network. And as is normal with the FIWARE data models, each of these entities has a number of different attributes or relationships that describe how all of the network components connect together and what their properties are. And again, this is very strongly based on how a network is defined and modeled in EPANET. So I've just got an example here of how a water distribution system would be represented using this data model. So this diagram shows how it would be represented in EPANET. So water distribution network is modeled as a set of links connected to nodes. So every link, that's the pipes, valves, and pumps, has a defined start and end node. And that just shows how the system links together. So this maps very nicely to a linked data format as used in FIWARE and the data models. So in a data model, this shows how the network would be represented. So each green box here is a different entity. So there's one for every link and every node in the network. And then you can see that every entity, or every link, sorry, has a starts at and an ends at relationship that connects it to some type of node. So this shows us how all of the components in the network are joined together. We can then add more detail for each component by specifying the properties of the entity. So a pipe, for example, has properties or length, diameter, roughness, minor loss, and initial status properties. And these reflect how it's defined in EPANET once again. And then for each of these properties, we can specify a value in units. So providing this information for every network component allows us to store all of the data contained in an EPANET input file relating to the physical network. So just quickly, a diagram here that would show how we would represent the whole of this network I just showed in the water network management data model format. So you've got every entity here is fully defined with all the properties, all the relationships, and all the values. So this is just a graphical representation of how the water network management data model works. So in practice, this is all stored in JSON format. So actually, it's going to look something like this. So this would be how our pipe entity is represented and how all the relationships and properties are defined. So when it comes to actually integrating EPANET with FIWARE, there are a number of things to consider. So firstly, any EPANET models that have previously been created for a network will have been stored as an EPANET input file. So this is a text-based file, but looks something like this. We've got different sections for each type of component, whether that's physical components like pipes or ones related to operation like patterns and curves. Got one line per component and various columns for the different attributes. And to integrate with FIWARE, we need to be able to convert this to the water network management data model format. So we can do this using the EPANET toolkit, which allows us to load an EPANET input file and extract all the data for the different components. And then with this information, we can generate some JSON for each network component in the format specified by the water network management data model. Secondly, once we've got this JSON data, we need to be able to store it using FIWARE so that it's easily accessible whenever we need to use it. So we can do this using, for example, HTTP post request to send it to a FIWARE context broker. So these two steps should be generally a one-off process for each network, unless there's major modifications to the network. So once we've done it once, we've got a model of the network stored using FIWARE, and this can be accessed in the future without any reference to the original EPANET input file, and any future modifications to the network can be made via the context broker without needing to use EPANET or create a new input file. So we've got this network model sat in the context broker, and while that's there, we might have other information going in from different sources that could update it. So for example, if any modifications are made to the network, for example, a pipe is replaced, we could update the data directly. We might also have data coming in from sensors in the network that could be used to update the network status or provide extra information. So for example, tank levels might be monitored. So next, whenever we want to do a simulation, we need to be able to retrieve the relevant current data from the context broker and use this to create an up-to-date EPANET model that we can use to run simulations. So we can retrieve all the network entities using HTTP requests. So that's going to give us a set of JSON-LD entities very similar to those we created originally from the input file, but hopefully updated based on the current state of the network. EPANET can't use this the data directly in this format, so we need to convert it somehow to form an EPANET, what's called an EPANET project. We don't actually need to recreate an input file for this, but instead EPANET's got a toolkit or a library of functions that allow us to add different components such as pipes, etc., and set their properties. So once we've done this, we can do whatever we want with the network model. So firstly, for example, we might just want to visualize the current state of the network. in which case we could just extract all the static data directly from the EPANET project. We might also want to run simulations based on the current state of the network. We might want to evaluate the effects of different interventions we're interested in implementing. So, for example, closing valves or applying some different operational rules or controls. So in this case, we can update the EPANET project using the EPANET toolkit. And we might also be interested in simulating different scenarios that don't necessarily match the current reality. So, for example, we could run some simulations based on forecasts, such as the demand, or possibly based on historical scenarios that have occurred, in which case we might have another link here with the context broker, for example, to pull out some historical demand data. So looking at further developments on this, so this integration of EPANET and FIWARE is still under development, and one of the other areas we're working on is extending the water network management data model to allow us to store additional information relating to the simulations that are run. So, for example, settings that don't relate to the physical network characteristics that we're storing at the moment. Like, for example, what time step we choose to use or how long we run the simulation for. So this is important if we want to be able to repeat simulations or know how a specific set of results was generated, particularly if we're doing lots of different scenarios and we want to make sure we know exactly what those were and what our results relate to. So I've got a bit of an overview here of the a new simulation entity we're working on, which should hopefully fully define a simulation. So first we would need to define what water distribution network we're actually modeling, because in the context broker we might have models for several different distinct networks, or we might just be interested in simulating part of a small part of a larger network. So we've actually got a network entity here, which defines which components belong to which network. And so then our simulation entity has input network relationship, which allows us to define which network we're modeling. We also want to be able to define what simulation options we're using, as I mentioned. So, for example, the duration of the simulation, what time steps we're using, what units, possibly what formula are used in the simulation. So these are specified here as properties, additional properties of the simulation entity, and we're using lists in this case, so it's fairly flexible, so you can specify lots of different options depending on the simulation. We might also want to simulate different operational strategies, and also we might want to make some modifications to the network. So if we want to see what was going to happen if we close a specific valve that is currently open, or if demand changes in one part of the network, we'd want to define this in the simulation entity so we know exactly what has been changed, and we can repeat this simulation if we want. And then also, yes, we might want to model different operational strategies, different controls, and again, we can define these in the simulation entity. And lastly, we might want to include some sort of description of the simulation as well, so not shown in this diagram. And okay, lastly, what next with this? So as I've said, integration of EPANET and FIWARE is still a work in progress. So this simulation entity I've shown is still under development. There's some further work to do to make sure this captures everything we might want to use EPANET for, and to implement it in practice. Also need to think about how we're going to integrate the simulation results with FIWARE. or how we store these results, or actually even if this is necessary, if we're already storing all the information needed to generate them with the simulation entity. And then the key step to make all of this useful is to make sure the EPANET model is integrated with sources of real-time data. So some things could be integrated quite easily. For example, the initial level of tanks or the status of valves. Other things such as demands could be a bit more complicated. For example, whatever meters we've got might not be very easy to map to the network model, or we might have to come up with a suitable way of dealing with missing data, for example. So that's an area for future development. And lastly, building on all of this, obviously we want to demonstrate how it can be used. We've got various case studies for this. We're looking at this in a range of projects, including FIWARE for water, Aqua3S, and Lotus. So thank you very much.